And by probably tonight, you'll get a copy of this. Let's see, do I have your email address for me to...
Yeah, I think you do.
You used the one you want me to use when you signed up?
Yeah, that works for me.
Okay. I'll send you a link tonight as to where you go to see that recording.
Okay.
All right. I do have one question. My other calculus book has a great page in it that has all 10 tests for convergence.
Yeah.
Starting with the nth term, I know you've had that one.
Yeah, we have.
Geometric series, I know you've had that one.
Yep.
Telescoping series?
We have not had that one.
Haven't had that one. P series?
P series, yeah. I think it's mostly P and the geometric that we'll be using.
Right. But I noticed that problem 8 is actually an alternating series. Have you had the alternating series yet?
I don't believe we have.
I don't think you have either, merely from the way the teacher answered this question. It looks to me like she used the geometric test here.
Yeah.
And that's not quite right, but it works. In other words, let's talk about the geometric test, okay? If I said x over 5 to the n, as n goes from 0 to infinity, and you said, well, what's the radius of convergence? You would let the absolute value of x over 5 be less than 1, correct?
Mm-hmm.
And then you'd solve it. And that's kind of what she did here. Okay? And for a geometric series, that's for sure. But for a P series, it's not as rigorous, or for an alternating series, I should say. But if you don't think you've had alternating series, let's not get bogged down in that explanation. The way she has done this is basically to say, notice one thing in these series that's very important. When you have an expression like this,
yep,
very important to be able to recognize that that is the fraction to the nth also.
What rule is that?
Well, they're both to the n power. The rule is basically a to the n. In other words, it's a rule of exponents. A over b to the n is the same as a over b to the n.
Okay, makes sense.
Okay? And that's key in some of these, to be able to know that. And this one is that way also. In other words, what we want to do is let this quantity on the right side, the absolute value of that, be less than 1. Okay? And it's only the function. I don't need the n there. I just know that if the absolute value of what's inside of there is less than 1, this is going to be a convergent series. Okay?
So is the interval of convergence -1 to 1 then?
No.
Or no?
In other words, it would be -1 to 1 if that was just x. But since x plus 2 over 5, then that's the quantity that has to be, or the absolute value that has to be less than 1. Notice that in her solution, that is the case. When x is greater in this interval from -7 to 3, then the absolute value of that is always less than 1.
All right.
Okay? And so by the geometric series, this would be convergence with that radius of convergence. Okay? And it's all about a typical geometric series maybe has a number there, and let's say you have a x over 4 there, okay, going from 0 to infinity. Well, this thing is going to be convergence whenever that is less than 1, or the absolute value of that. So x could be 3. So the interval of convergence might be -3 to, or -4 to 4.
Okay. And with the interval of convergence, is it always set to be less than 1? Is 1 always the number
When
that
you're
is
dealing
less than?
with a geometric series, if I told you we have this, obviously when x is greater than 1, that series does not converge, right? I mean,
Okay, yeah.
put in an x of 2. You have 2 to the 1th plus 4 plus 8 plus 16. That's doing nothing but going up. So if this number is greater than 1, it is a divergent series. If that number is less than 1, let's say that number is 1/2, well, that's a convergent series, because notice that as n counts up, the number gets less and less. In other words, that series becomes 1 plus 1/2 plus 1/4 plus 1/8. We already know from the very beginning of this chapter that that is a convergent series.
Okay. Okay, get that.
The P series, basically. But basically, the one you focused on the most is a geometric series, and the absolute value of this number, if it's less than 1, it converges. If it's greater than 1, it diverges. Okay, so that's the most important thing. So if I replace that with something like x over 4, well, now I have to say the absolute value of x over 4 has to be less than 1. Which means x would have to be greater than -4 and less than 4. That's the interval of convergence. Notice that if x were 5, then we would have 5 over 4 to the end. That blows up. That diverges.
Yeah.
If x is less than 4, then this number, x over 4, is going to be less than 1. Any number less than 1 is going to converge. All right, let's not spend too much time on any one of these. We could probably spend an hour on every problem here. But anyway, what she does is, that's a little bit of fancy math. You follow that algebra? It's not that fancy. She just turns the denominator, finds a common denominator, flips and multiplies, and now she has this number that has to be less than absolute value 1. And that's how she comes up with that answer. All right. Number 9. Look at my here. 9's pretty straightforward, pretty easy.
Yeah, I got none. I didn't have too much trouble with that one.
I don't think you need any help with those. We did enough of those the other day. Just about.
Yeah, when it's just the Taylor polynomial, I don't have too much trouble with that.
All right. Well, right. That's not a Maclaurin, but it's Taylor. So the biggest difference is you have to add or use, instead of just x, it has to be x minus whatever it's centered at.
Yeah.
Okay. Now, figuring out the final term might not be so easy. Let's see. I didn't do that. I got another one where I did do that. Let's wait and talk about that when we get to 11. 10. Also extremely easy. 10's no different than 9, right?
Yeah.
And it's even easier because 10, they only want the third degree Taylor polynomial. If you ask me what the difference between a Taylor polynomial and a power series was the other day, power series is just an infinite series of polynomials with coefficients. It's an infinite sum of polynomials with coefficients. That's what a power series is. In other words, x plus x squared plus x cubed plus x to the fourth dot 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 x to the nth. That's a power series. But a power series is an infinite series, as opposed to a Taylor polynomial where you can have a third degree. If you took a complete Taylor polynomial, then that's the same thing as a power series. But if I take just the third degree Taylor polynomial, then it's a finite series. It's not an infinite series. And this one, pretty straightforward. That's f of a right there. It's 5. There's the minus 3 coefficient for the second term times x minus 1, because the thing is centered at 1, because of what that says. Write the third degree Taylor polynomial for h, where h of x equals the integral of this function about x equal 1. So what we're going to do is, the way we integrate p of x, we know what p of x is. Well, we're going to integrate it term by term. Okay, we're going to integrate the 5, that gives us 5x. We're going to integrate this term, gives us minus 3/2 x minus 1 squared. You see that? And this term is the integral of this term, and this term is the integral of this term. One of the things that makes infinite series so powerful is the fact that you can integrate it or differentiate it, and you can do it term by term. Remember how much easier it is to integrate the sum of stuff than it is to integrate the product of stuff. When you're integrating the product of stuff, it's a bear. You got to find all kinds of interesting techniques to use in order to integrate it. But if you're integrating the sum of a bunch of numbers, it's generally just going through and using the power rule on each term.
Yeah.
And that's all they did here. And as far as their terminology here, this is called a dummy variable, p of t. But you know from the fundamental law of calculus that the integral from 1 to x of p of t is p of x.
Okay.
So,
and did you, would the 0 term be excluded because the integral starts at 1?
No, the 0 term was not excluded. There it is right there in p of x. Right? The 5?
Okay. Yeah.
Okay.
But on b, with
when I integrate that, it becomes 5x.
Okay.
The integral of 5 is 5x. So that's all this term is the integral of this term. And this second term is the integral of this second term. If you integrate each of these 4 terms in this third degree polynomial, you'll get these 4 terms down here.
Okay.
Okay.
I see.
Okay, number 11. 11, the first 4 non-zero terms for that expansion. And she's listed them. So there's not a whole lot of work to do. This is no more difficult than anything else. We're going to do the f of 0, which is 1. And then we're going to do the f prime evaluated at 0, and that's going to be minus 2x squared, and so forth and so on. Any questions about that? Now, I did take this one step further and come up with the nth term.
Okay.
It's actually pretty easy. Can you figure out what the nth term would be? In other words, let's write it out here.
Negative 2x squared. Would it be negative 2x squared to the n over n factorial?
Well, we can see it's an alternating series, right?
Yeah. So there's probably a negative 1 to the n.
Always there's going to be, you designate alternate series by a negative 1. So what I came up with, and sometimes there's more than one solution, but what I came up with was this.
Yeah.
That seems to fit everything. In other words, this takes care of the plus minus, and this takes care of these exponents. In other words, that is to the 1, that's squared, cubed, n factorials underneath. So this one's pretty easy to come up with. Taylor polynomial, very straightforward. In other words, this very first term is f of a when a is 2. And that's minus 3. So that's where this minus 3 comes from. The rest of it is... And a third degree polynomial, Taylor polynomial, does mean you go out until that first exponent is 3, and the factorial is that same 3. I didn't see anything interesting about 12 at all.
No, I'm good with that one.
Okay. 13. Find the coefficient of the x minus 8 squared term. Okay, so we know the x minus 8 squared term comes when we got a 2 factorial under there, right? So that's the third term of the Taylor, it's the third degree Taylor polynomial, and that would be the third term of it. Oh, well, that would be the second term of it, excuse me. So, all right. So the first thing they do is find f prime of x, which is 1 over x. You know, the derivative of natural log of x is 1 over x. Second derivative is minus 1 over x squared. The second derivative evaluated at 8 is minus 1/64th. And the coefficient of the of that term, that's x minus 8 squared, has a 2 factorial on it. Well, there's your minus 1/64th. So the coefficient is, in effect, minus 1 over 128.
Okay. It's not too hard.
No, this would actually, she's taken some shortcuts here, which, good for her. She didn't want to give you all the answers. But if you lay out the first 2 terms, in other words, all you need to do is calculate the second degree Taylor series for this function, centered at 8. And that is the last term of the second degree Taylor series. And
all right.
You always know the coefficient is the second derivative evaluated at that number. So the second derivative always matches up with this squared, always matches up with this 2 factorial. (14) is a typical p-series. Now, let's talk about this just because there's some very interesting stuff in this. If I take this series here, this is the way your book starts out, that converges. This one diverges. Now that's got to be interesting to you, because it took me months thinking about this before I could wrap my head around how the top one could converge and the bottom one could diverge.
Yeah.
Particularly when you notice that the bottom one, what's the nth term go to?
+1.
0, right?
0. Yeah.
Well, the nth term means that if I carry this out to infinity, I'm going to have 1 over n as n reaches infinity. 1 over infinity is 0. In other words, the last term of this bottom series is 0. And the last term of the top series is also 0. And you've had the nth term test. The nth, for a series to converge, the nth term has to be 0. However, the reverse is not true. Just because the nth term is 0 doesn't mean the series will converge. It is just a necessary condition. In other words, both of these series that I've written, the nth term is 0, but only the top one is convergent. Now, why is that? Because the top one is 1 over x squared, or 1 over n squared. And the bottom one is 1 over n. And here's what a p-series says, is that if this p right there is 1 or greater, if it's greater than 1, this series will converge. If it's 1 or less, it will diverge. Notice that in this series right there, p is exactly 1.
Mm-hmm.
I've got 1 over n to the 1 as n counts up. So it's 1 over 2 plus 1 over 3 plus 1 over 4. Whereas in this one, p is 2, right? As long as p is greater than 1, the series will converge. In other words, if I even had this kind of series, 1 over n to the 1.00001, that series converges. Just like 1 over n squared converged. But 1 over n diverges, or 1 over n to the 0.9 power diverges. So if that exponent, whether it's greater than 1 or less than 1, makes all the difference in the world. And that's why this series converges and this one diverges. Because p is greater than 1 up there. So, looking at 14, we know we're going to have a convergent series as long as that exponent is greater than 1. So the solution is to set that exponent, p plus 1, being greater than 1, which makes p greater than 0 be the solution. So if her notes here are a little confusing. This p she's written down here is not the same as this p here. This p is the general p relating to this series. In other words, in a series like this, if that exponent is greater than 1, it converges. Well, in this case, the exponent is p plus 1. They'd have been better served if they'd have used a different variable here than p. They should have said if z plus 1 is greater than 1. So if z is greater than 0, you have a convergent series, because then that exponent is greater than 1. 15 is very standard integral, just straight power rule. I'm not quite sure. I guess I don't know why she has all of this stuff over here. I mean, am I missing something here?
She had done that one in class and said she included it because, let's see, at one,
I don't think
there's a domain error.
need to do any of this stuff over here. Well, maybe, I guess. Well, let's see.
She split it into two because at one, the denominator equals
I see that now, that the denominator would be 0, so that's not in the domain. But there's nothing that prevents me from applying the power rule to that. X minus 1, I'm going to add 1 to the exponent, divide by the new exponent, and evaluate it from 0 to 3. Well, when I evaluate it at 3, I get 3 times the cube root of 2. And when I evaluate it at 0, I get negative 3 times the cube root of minus 1, which is 1. So it's 3 plus 3. And I think she's got a typo here. That should be cube root of 2. Right? I mean, we're starting with 2/3. We're going to end up with 1/3 there. This answer here will produce this exact answer, only it's cube root of 2.
Okay, keep that in mind.
Yeah.
Much easier way to go about it.
Well, I'm not sure why she went to all this trouble. Like you said, she's approaching...
Maybe she didn't realize you can do it your way.
Let me think about this for a second. You do bring up a good... Oh, I see what she's doing. We can't actually cross that because it's not defined at 0, or at 1 rather. We have to go from 0 to 1 from the left side, and then go from 1 from the right side to 3. In other words, we have to do it in 2 pieces, which is what she's done here. In the left side, she's going from 0 to 1, approaching from the left. And then the second one, she's going from 1, approaching from the right, to 3. And that covers the full domain from 0 to 3 without crossing the point where it's not defined. You can't actually integrate straight across there. I don't think it makes any difference to the answer. She still has a typo here. In other words, when she does, unless I'm mistaken, maybe I didn't give it enough thought, but she's still going to end up with cube root. There's no way to integrate that without ending up with cube root. She wrote square root. Well, you know what? Maybe I'll bet this 3 belongs right there. Yeah, my answer was 3 plus the cube root of 2. Or was it? Yeah, it was. In other words, if I take this answer right here and factor out a 3, I get 3 times the cube root of 2 plus 3. Or plus 1, rather, which is the same thing as that. And in other words, I don't think the way she did it gives you a different answer. It's more technically correct.
Yeah.
16, when you're doing improper integrals, in other words, where one of the limits of integration is infinity or negative infinity, the book always use a technique that I don't find necessary. In other words, I just go ahead and make it go from negative infinity to 3, and it works just fine. You don't need to use a letter and then take the letter or the limit as that letter goes to negative infinity. It just isn't necessary. First of all, do you have any trouble integrating that expression?
No.
By partial fractions, it's not that obvious to do at all. You want to go through it?
Yeah, sure, why not?
Well, you should know how to integrate by partial fractions. It's one of the harder techniques. Let's do one. If I'm trying to integrate this expression, and I can turn this part into two things being added or subtracted, it'll be a lot easier to integrate. Well, the method of partial fractions begins this way. Okay. Partial fractions basically is taking something that's been found a common denominator of and separating it into its two original fractions. Well, these two, if I gave you those two fractions, you would add them together by finding a common denominator and figuring out what the numerator was, right?
Mm-hmm.
Well, so what that means is that 1, this numerator over here, has to be equal to a times x minus 2 plus b times x plus 2. Because the denominator is going to be the same. In other words, when I add those two together, I've got the same common denominator as I have on the left side. Therefore, the numerators have to be equal. And the numerator on the right side is going to be what I have written on the right here. Okay. Now, to solve this equation has to be true for all x. So I can conveniently solve it by, first of all, letting x equal 2. If I let x equal 2, the a term disappears, and I end up with 4b equals 1. Did I do this right? Hold on. I might have it backwards. No? Okay. So I get b equals 1/4. And then if I go back and I want to let x equal minus 2, which I can do since the thing has to be true for all x, well, that makes that term disappear. And I end up with negative 4a equal 1. So a ends up being negative 1/4. So now I can go back to this step here, and I have a is negative 1/4, b is positive 1/4. If I gave you those two fractions to add together, you would find a common denominator and you would come up with what's on the left. So what I've essentially done is decomposed the fraction. And what's the advantage of that? Well, if I want to take the integral of that, it's hard. I got multiplication going on.
No, you can
But
separate it into
I have
integrals,
separated
right?
it into two things that it's very easy to take the integral of. This left integral is minus, I can take the minus 1/4 out. What's left over? Natural log of x plus 2. On the right side, I can take the 1/4 out. I get natural log of x minus 2. And now because I have the difference, I've got this minus that. I'm going to turn it into one log function only. And I'm going to factor out the 1/4. And I end up with the natural log of this in the numerator, x minus 2, divided by x plus 2 in the denominator. In other words, I combine those into one log function. Okay, so that's the answer. Now I have to evaluate that. And they want to go from negative infinity to negative 3. Nowhere is there a problem. In other words, between negative infinity and negative 3, I don't have the denominator become 0. I don't have the numerator become 0. Now, this is where I was talking about that if I'm trying to evaluate that, it's pretty easy to evaluate without using this technique that she wrote. Just plug in the numbers. In other words, we have 1/4 natural log of minus 3 minus 2 all over minus 3 plus 2 minus, put this 1/4 out there. Now I'm going to evaluate it at that. Okay, well, how do I evaluate that? Natural log of negative, I'm just going to use negative infinity minus 2 all over negative infinity plus 2. And now I can see why they use the other technique. In other words, usually you can figure out what these are pretty easily. The technique they used was they let the letter A be infinity. And if I have the letter A there, and I say, what is the limit of that thing as A goes to negative infinity? It's the ratio of the coefficients, right?
Mm-hmm.
So it's the natural log of 1, which is 0. So this whole term goes to 0, and I can get rid of it. And so this is the answer. What is that? The natural log of minus 5 over minus 1.
Natural log of 5 times 1/4.
Yeah, and there's the negative. Somehow I got these reversed. I'm not sure how that happened. She ended up with X. No, she's got the same answer. X minus 2 over X plus 2. Yeah, and she ends up doing this evaluation where she's let A represent the negative infinity. And that's where I made my problem. As I went to negative 3, I got to go to 3. I wrote it wrong. Yeah. Oh no, it is negative 3. She changed it to 3.
Where'd you do that? Oh, yeah.
I'm not sure whether she just did a typo or what. Because my answer came out 1/4 the natural log of 5, not 1/5. And I think maybe she's getting 1/5 because she let that be 3 instead of minus 3.
What's the rule involving the reversal of the limits with the negatives where can't you flip them?
Yeah, if you flip the limits.
I mean, that's not what she did, but
it's the you wouldn't do that here because you'd be going from minus 3 to minus infinity, so it doesn't really help things. No, what they're doing here is technically correct. In other words, it's difficult to evaluate that at negative when x is negative infinity, right? Mm-hmm. How do you evaluate it? But if you let x be a, and as a goes to negative infinity, we know the limits or the ratio of the coefficients, which is 1, and so that's how she gets natural log of 1.
So what you did was you just treated infinity like a variable?
Exactly. In other
Okay.
words, it's a much ado about nothing in terms of doing that. But if you do treat infinity like a variable, usually it's fairly straightforward. You know, if you have the square root of infinity, that's going to infinity. I don't need,
Yep.
in other words, if, hold on. I want to know what the square root of x is as x goes to infinity. To me, that's the same thing as the square root of infinity. Well, the square root of infinity is infinity. So I could have started out just with the square root of infinity right off the get-go. I know that that's an infinity. But where it might be useful is when you have something like x minus 2 over x minus plus 2. And now it's not as clear what the limit of that is. But it's still the ratio of the coefficients, 1 to 1, or negative 1 to negative 1, which is 1. Partial fractions, incidentally. Have you gotten to doing? You must.
Yeah, we've done partial fractions.
And they can get much, much tougher than the one that we did here.
Yeah.
You can have 3 things in the bottom, and one of them can be a quadratic, and they can get extremely tough. Hopefully, they won't get any tougher than this one on your test. Let's see. And yeah, you have to use partial fractions on this. There's no way not to avoid it. Whenever you see either a quadratic in the denominator or the product of some linears or even the product of linears and a irreducible quadratic, you know you're going to have to use partial fractions. All right. This one is interesting. We're going to use the comparison test. Okay. Basically, let me just graphically describe the comparison test. If I have a function like that I know converges, and I can find another function that's always less than this function. I don't know what the other function does, but I know it's always less than the top function. Then it also has to converge. It can do nothing but converge. Now, it's important to keep it straight. If the top function diverges, then we don't know what the bottom function does. Right? In other words, if the top function diverges and goes off to infinity, we don't know what the bottom function might converge, it might diverge. But as long as the bottom function is less than a convergent function, it is convergent. And on the other hand, if I know the top function is divergent, and I can find another function that's always greater than the top function, then it also has to be divergent. Okay, so you understand the logic of that?
Yeah.
Okay. In this case, we're going to use the comparison to prove that converges or diverges. And the comparison function she uses is 4 over x to the 5th. Now, you see why that's used? Because the domain of sine, well, the domain of sine or the range of sine is negative 1 to 1. It can never be less than negative 1. It can never be greater than 1. Therefore, 3 minus the sine of any angle has to be less than 4. Less than or equal to 4.
Yeah.
Okay? So this function on the left, by definition, about what we know about sine, has to be less than this function. This function is a straight p-series. I can factor the 4 out of the integral, and I'm left with 1 over x to the 5th, which is a p-series. Since p is greater than 1, it's convergent. Since 5 is greater than 1, by the p-series test, it's convergent. Since this series is convergent, and this series is always less than this series, then it's also convergent. Now, if we go back to my drawing, it's not actually necessary if, let's go back and draw a function that we know is convergent. Okay. Now I'm going to draw another function, but this function is actually bigger than that one up to a certain set of numbers, maybe up to the number 3. It's greater than the first one. But as long as you go out a long ways on the x-axis, the blue function is always less than the red function, then it's convergent also by the direct comparison test. So it doesn't have to be less than for the entire domain. It has to be less than for some x value greater than some number. That's all.
Okay.
Okay. And there's lots of functions where this might be greater than the red function through the first 2 or 3 numbers. But as soon as you get beyond the number 3, the blue function is always less than the red function. And if we know the red function converges, so does the blue one, even though the blue is bigger than the red in the early going. It's kind of fun to review some of this stuff. I hadn't reviewed it in a long time, and it started coming back, and this is interesting stuff for sure. Find the area of the first quadrant. Well, that's the integral from 0 to infinity, right?
Yep. Yeah.
Or, as they put it, from 0 to a, taking the limit as a goes to infinity. Well, what's this method that they're using here called?
U substitution?
Actually not. This is integration by parts.
Or the UV equals...
Well, integration by parts is no easy thing to get a handle on.
It's what? Integral ddu?
Yeah, exactly. Well, it's the interval of u dv. In other words, the way to memorize it, and let me go back to red. Kind of a clever way to memorize it. The whole integral is equal to uv minus the integral of voodoo. Okay, what goes on the left side? The reverse of that. The integral of u dv. So if you're trying to take the integral of u dv, then it's equal to u times v minus the integral of v du.
Mm-hmm.
Well, the secret is, what do you make u and what do you make dv? And I don't know if you were taught this. We probably
did Lipit.
Lipit, exactly. I love Lipit.
Yeah.
Okay, so logs, inverse trig, polynomials, exponentials, trig functions. Well, in our case, we have e to the minus x times x. E to the minus x times x dx. Well, according to Lipit, what am I going to let u be?
E to the negative x.
No, that's the exponential. It comes before p, which is polynomial. So because the polynomial becomes before the exponential, I'm going to let the polynomial be u.
It's considered a polynomial even with just one term?
Yes. Yes. A polynomial is any series of, x plus x squared or just x. Even a constant is actually technically a polynomial. But so once you've decided what to let u equal, everything else is dv. And this is the part that's a little confusing, but not if you think of it like that. In other words, figure out what to let u be based on Lipit, and then everything else in the expression equals dv. Okay? And now I'm going to differentiate the left and integrate the right. And I'll show you why. Because remember, my formula is the integral of u dv equals uv minus the integral of voodoo. So I need to come up with, there's my u, which is now x. So uv would be x. There's v. In other words, you have to solve for all of these in order to answer this. And finally, the integral of v, well, that's the integral of minus e to the minus x. Du is dx. And now I have an integral that I can integrate. That's easy to integrate. In fact, I'll pull the negative signs out, so I'll make that a positive. And now my answer is minus x e to the minus x plus, well, the integral of that is negative e to the negative x. Biggest thing you've got to be careful about on some of these is you end up with an expression that has 18 negative signs in it. And it's really, really easy to lose one of those negative signs and let it turn positive. And of course, one mistake is all it makes. Is all it takes to miss a problem. And you can see that's what she's done over here. She's let u equal x, dv, everything else. She's done exactly what I did. She got this answer. And then to evaluate it from 0 to infinity, she pretty much takes her answer and substitutes a for infinity, or for x rather, and solves this limit problem. Whereas it's just as easy to solve if, notice that if I make that infinity, then I have infinity over infinity. It's not real clear what this limit is. Right? Isn't that an indeterminate?
Yeah.
You end up with negative infinity times e over infinity. That must be 1, because this is, let's see, e to the minus infinity is 0. So this has to be 0. But she doesn't show why. I'm trying to think, could you use L'Hopital's rule? I don't even think so. If I had x over e to the x.
Well, because it's not a quotient, is it?
But L'Hopital's rule will show that goes to 0. It is a quotient. In other words, excuse me, I gotta be careful about going over here. I do have a 4 o'clock. If I said negative infinity times e to the negative infinity, well, that's the same as, that goes to 0. In other words, that's what this expression is, right? Substituting infinity for a, I end up with this. That's got to go to 0. The bottom blows up much faster than the top does. And this goes to 0, so you have 0 minus 0 plus 1 equals 1. So that's the way they get that. Let's see if we can take a quick look at 19. 19 is fairly straightforward. 19 is U substitution. Okay. Now, the only thing unusual about 19
is... They're both in the denominator, right?
Exactly. And the reason that's unusual is because notice the derivative of natural log x is 1 over x, which means that it ends up in the numerator. And canceling out that x. So usually when you have something like, let's say I had the sine of x squared, and I had a 2x like that, I can just use the power rule on that. Because u would be x squared, the derivative of that is 2x, the derivative is going to end up in the denominator, taking out my 2x, leaving just sine of u. So the answer would be negative cosine of x squared. In other words, most of the time you're using u substitution, that's in the numerator, the derivative of your u. But when your u is natural log, as it is with this one, the derivative of that, watch what happens. I'll do it real quick. I'm going to let u equal natural log of x. So du dx equals 1 over x, and du times x equals dx. So when I go to substitute for dx, I'm putting that in. Notice my x is in the numerator. So this integral is going to become 5 x du all over x u to the 4th. The x's go away, which we have to have them do, and now we have an integral that's easily done using the power rule. Okay. So whenever you see a natural log function that you know that you're going to have to let u equal that, well then look for the derivative of that to be in the denominator, not the numerator. And of course, once you integrate it, this 1 over u to the 4th, that integrates to minus 5/3 u to the minus 3rd. And as that goes to infinity, it ends up going to that number.
All right.
Natural log of infinity. Natural log of infinity is infinity. Natural log of e is 1. So it's not hard to evaluate this thing, even without using this technique. In other words, I would just go ahead and write that, write infinity there, and evaluate it, because we know how to solve this. 1 over the natural log of infinity cubed is 0. Minus a minus 5/3 gives you your 5/3 answer. All right. Well, good luck with the rest of that chapter. It's going to be challenging.
Thank you.
It gets almost exponentially harder as you get into it. But feel free to schedule an appointment if you like this online session. We can do them all online. If you feel like you want to meet in person again, I'm happy to meet you at that library if you like.
All right.
But I'll let you handle it. You've been on my website, so you know how to schedule appointments. And
yep.
I'll try to get the recording of this thing to you by tonight.